The first problem on the worksheet for Chapter 14 involves us calculating ppm. ppm stands for parts per million, and it's a mass-based unit. We can think of ppm as being equal to the milligrams of our solute to the total kilograms of solution. So in this question, we're told that we have 0.0079 grams of strontium 2+ per kilogram of water. Well, we can actually think of our kilogram of water as actually being the total mass of solution, because the mass of our solute isn't really going to make a big difference here. Right? Our 0.0079 grams is going to pale in comparison to our kilogram of water. So all we need to do is convert our grams of strontium to milligrams to solve this problem. There are 1,000 milligrams in a gram, so if we take our grams of strontium 2+ and multiply it by 1,000, our grams will cancel out, and we'll be left with 7.9 milligrams of strontium 2+ per kilogram of solution. Same thing as saying we've got 7.9 ppm. Number 2 is another problem based around determining the concentration of a substance. It's a more complicated problem than we've seen in the past, but it still operates off of similar principles. So in number 2, what we're given volumes of two different components of the solution. We're given a volume of a solute, our CH3OH, and we're given a volume of our solvent, which is acetonitrile, which is CH3CN. We're also given densities of these substances, and we're asked to calculate the mole fraction of these two things. Again, just to review, mole fraction is moles of whatever substance we're talking about. We can call it substance A over total moles. So to solve this problem, we're going to need to know what the moles of our solute is, our CH3OH, and we're going to need our total moles of solution, which means we're going to need both our moles of CH3OH and our moles of CH3CN. We're going to need to do two conversions for each of these. Because we're starting with volume, we need to get to grams before we can get to moles, because we know what conversion factor we use to get from grams to moles, and that's molar mass. So to get from volume to mass of something, you use density. Right? Density is equal to mass over volume, and you can treat it as a conversion factor. We're starting off with 22.5 milliliters of CH3OH. We're told that the density is 0.791 grams per milliliter. If we multiply by the density, our milliliters will cancel out and be left with grams. If we stopped here, we'd have grams of CH3OH. We could use that if this problem involved calculating percent by mass. But we have to go one step further because we're calculating moles. Again, you use molar mass to do that. We're going to divide by molar mass because we want to cancel out grams. The molar mass of CH3OH is 32.042 grams per mole. Doing the math here gives us 0.555 moles of CH3OH. We can take similar steps with our CH3CN. We go from our volume to mass using density. Multiply by density cancels out milliliters. We can then go from grams, our mass, to moles using the molar mass. If we divide by the molar mass of CH3CN, which is 41.053 grams per mole, you get 1.89 moles of CH3CN. Now that we've got the moles of our solvent, we can plug them into our mole fraction equation. So our mole fraction equation says that we should have moles of CH3OH on the top and total moles on the bottom. We can set it up as follows here. Doing so will give you a mole fraction of 0.227. Question number 4 is another colligative properties problem, and specifically this one deals with vapor pressure lowering. So this problem incorporates some stuff with Chapter 14 with some things we actually learned earlier in the year. We're told we're mixing equal masses together of water and of ethanol. And we're given the vapor pressures of the pure substances of pure water and pure ethanol at a certain temperature, and we want to know what the vapor pressure of this solution is going to be at the same temperature. So the formula for vapor pressure lowering is depicted here. Right? The new vapor pressure of our substance in a solution is equal to the mole fraction of that substance in the solution times the vapor pressure of that pure substance. So we're going to combine this vapor pressure lowering with Dalton's law of partial pressures. The total vapor pressure of our solution is going to equal to the sum of the vapor pressure of the two components in our solution, of water and of ethanol. So the first thing we need to do here is we can pick any mass. Right? We're mixing equal masses of the two substances, so you can pick any mass. and say, okay, we have that mass of each of these substances. I pick 100 grams, right? You could use 50 grams, you could use 700 grams, you could use 3 grams, whatever. I picked 100 here. So we need these masses because we need to figure out the moles of each substance, and we need to figure out the moles of each substance because we need to know the mole fractions of each substance to use in our vapor pressure lowering equation, which is called Raoult's law. So if we have 100 grams of water, that's saying the same thing as we have 5.55 grams of water. If we have 100 grams of ethanol, it's equal to 2.17 moles of ethanol. You go from grams to moles using the molar mass. Okay, if we divide by molar mass, we get those values. From here, we can calculate the mole fraction of each of these substances. Okay, mole fraction is equal to the moles of our substance, so whatever we care about, moles of A, divided by the total moles. So we've got, for instance, for water, we've got 5.55 moles of water. We've got 7.72 total moles of our solution. You get that by adding our number of moles of water by our number of moles of ethanol. Okay, dividing our moles of water by our moles of ethanol gives us a mole fraction of water of 0.719. Now our two mole fractions need to be able to add up to 1, right, because they need to add up to the entirety of the substance. So we can calculate our mole fraction of ethanol in two ways. One, using this formula here, right, moles of A plus moles of A divided by total moles. Or the other way we could do it would be subtracting our mole fraction of oxygen from 1. They'll yield the same answer here. They'll yield a mole fraction of 0.281 for ethanol. From here we can use this Raoult's law to figure out the vapor pressure of each of our components. Right? The vapor pressure of water is equal to its mole fraction, 0.719, times the vapor pressure of pure water at this temperature, 175 torricellis. That'll give us a vapor pressure of water in our mixture of 126 torricellis. Doing the same thing with ethanol says that the vapor pressure of ethanol in our mixture is 112 torricellis. The total vapor pressure is the sum of those two things, or 238 torricellis total. Problem number 5 is yet another colligative properties problem that's a little bit more straightforward. We want to know what the osmotic pressure is if we dissolve 44.2 milligrams of aspirin in 358 milliliters of water. Okay, this is the formula for calculating our osmotic pressure here. It's that the osmotic pressure, which we abbreviate using capital Pi, equals the total molarity of solute particles times the ideal gas constant times the temperature in Kelvin. It looks kind of like the ideal gas law. Okay, so to solve this problem, we need to figure out what the molarity of our substance is. Okay, we can do this by setting up our fraction as follows, right? We've got our grams of aspirin in the numerator, and we've got our liters of water in the denominator. We can assume that these volumes aren't necessarily additive and that the total volume of our solution is going to be the same as our volume of water. That would mean that our 358 milliliters of water is our total solution volume. Remember that molarity equals moles of solute divided by liters of solution. We say our total volume of our solution is 358 milliliters. It's the same as saying our total solution volume is 0.358 liters because there are 1,000 milliliters in a liter. Okay, we have to work with our numerator then. We've got to go from grams of our solute to moles of our solute. Going from grams to moles involves using molar mass. So what we're going to do here is we're going to divide our grams by our molar mass of aspirin. Doing so, we'll cancel out grams of aspirin and we'll be left with moles of aspirin. Our fraction then becomes our molarity, which is 6.85 times 10 to the negative 4 moles per liter. From here, we can plug this into our formula. We can say that our vapor pressure, sorry, not our vapor pressure, our osmotic pressure equals the molarity that we just solved for times the ideal gas constant. My pressure is going to be in atmospheres, so I'm going to use 0.0821 liters times atmospheres per mole times Kelvin as my R, times the temperature in Kelvin. Right? If our temperature is 25 degrees Celsius, that's the same thing as saying the temperature is 298 Kelvin. Plugging these in gives us an osmotic pressure of 0.0168 atmospheres. In problem number 6, we're given a change in freezing temperature, and we're given a mass of our solvent, and we're told to solve for the molar mass of our solute. So this problem can be kind of confusing, but the key here is to break it up into different steps. This problem involves freezing point depression. So the key is you're going to have to use the formula for freezing point depression somehow. And this formula is depicted here. The change in freezing temperature equals the freezing point depression constant times the molality of the substance. We know what the change in freezing temperature is. Right? We're told that change is negative 1.4 degrees Celsius, right, given our initial and our final freezing temperatures. You can then look up the freezing point depression constant, which is 5.12 degrees Celsius per molality, or times mole per kilogram. We can plug these into our equation and solve for molality. Our molality is then 0.27 moles per kilogram. That's moles of solute per kilogram of solvent. We're also given our mass of solvent. We're told that we've got 0.1 kilograms of benzene, and benzene is our solvent here. Okay, if we take our mass of solvent and multiply it by the molality, because again, molality is equal to moles of solute per kilogram of solvent, our kilograms of solvent will cancel out. And what we'll be left with is the number of moles of lauryl alcohol that we have. Again, lauryl alcohol is our solute. So by multiplying our molality that we determined using the freezing point depression formula by our mass of solvent, we get our moles of solute. We're also told our mass of our solute. We're told that we dissolved 5 grams of lauryl alcohol in our 0.1 kilograms of benzene. Key to remember here is that the units for molar mass are grams per mole. So if we know our grams and we know how many moles we have, we can solve for the molar mass. Okay, in the previous step, we determined how many moles we have. We've got 0.027 moles of lauryl alcohol. We're also told that we have 5 grams of lauryl alcohol, so we just divide one by the other and you get a total of 185 grams per mole.